On the menu today, parallel plates and the equations that are unique to the uniform field situation between charged parallel plates, and yeah, all that stuff. And then eventually motion of charged particles in electric fields. Later on, will be in varying electric fields, but the nice thing about parallel plates is it's a nice uniform electric field. We're going to look a little bit at that contradiction. So this is now going to be, we're going to transition into the one that has a voltage applied across the plates with a battery. So a little explanation of the contrast or apparent contradiction between the two things that we've been talking about. We originally were told that the distance between the plates doesn't matter as long as it's not crazy big in comparison to the spacing or the width of the plates. And so now we're going to have an equation that's going to say, oh, it's equal to the voltage across the plates, the potential difference across the plates, divided by the distance between them. Exact opposite. So we'll look at that, and we'll also look at a related topic called the Millikan's oil drop experiment. So the Millikan oil drop experiment is one of those classic physics experiments that really was a monumental moment. So it's to do with how Millikan discovered the charge of an electron. Right up there with Rutherford's gold foil experiment and stuff like that. So hopefully remember Rutherford's experiment was about the nucleus being super small, right? So just to remind you what we've talked about, if you have just charge built up on plates, then they're a distance r apart and so on is charge built up. But the electric field intensity, which remember is how much force per charge there is, it's how strong the field is essentially, right? Only depends on the quantity of charge built up. It does not depend on the distance between the plates. Whereas you are going to see today, if you have a voltage applied across the plates, so there's a potential difference across the plates, then the electric field intensity is actually delta V, like the voltage across the plates, over the distance between. Right? So it actually completely depends on the distance between the plates. And it's odd that these, you have that distinction, but we'll look at it and hopefully make it make sense to you. So here we go. Here's the plates with an applied voltage across, and yeah, like the electric field between the parallel plates is uniform still. All familiar stuff, really, so far. Nothing else really going on there. So remember that V is potential, right? So that's energy per charge. Electric potential is energy per charge. I'm really going to use this as an opportunity to review all these important concepts that I want you to help keep, at the forefront of your mind, if you will, right? Like, you shouldn't just see V. You should be thinking, oh, that's energy per charge, joules per coulomb even, right? So I could even add that in. I don't have my touch screen right now, but joules per coulomb. So like that, right? Like, it doesn't look as good as it would if I could just write it in, but good enough. Which is technically the same thing as a difference in energy per coulomb, but it's just from a zero value at infinity, right? So it's kind of like potential difference, but really it's just electric potential. And then electric potential difference, delta V, is the difference between two local spots, right? And so rather than the difference between infinity and a local spot. So, when we look at V, potential itself, right, it's energy per charge, then delta V is the change in energy per charge, right? So that could solve to be electric potential energy, QV. And then change in energy is QV final minus QV initial, if you will, giving us a Q delta V, right? It's basically just slap a delta V on both ones, but this shows why it's true. And so, yeah, that's electric potential difference, right? So I'm talking about this for one purpose of reviewing the ideas and keeping them fresh in your mind, but also to point out that when we talk about voltage from a battery, we're going to correctly refer to it as delta V. It's the change in the electric potential, or in other words, we call that the potential difference, right? Whereas people tend to just describe the battery voltage as just, it's 9 volts, right? And you start to think of it as just V rather than delta V, right? As you think of by accident as electric potential V versus electric potential difference, the difference between them. So yeah, derivation here of the electric potential difference equations that are, unique to parallel plates. We're going to look at the work equals force, or force times distance, force times displacement concept. And so as we saw here, the distance between the plates is r, so that's our delta d. And so we have our, fr. We have the luxury in this simple analysis here that it's a constant force, right? And so we don't have to worry about calculus or complicated things. It's just literally force times the same force the whole time times that whole distance, right? So to do with force, if you're talking about, if you want to work ahead in a development here about work equaling force times distance, you're going to need to think about, well, what's the force, right? Well, the force in an electric field is to do with the field intensity. Curly E is that field intensity, which is the electric force per charge, right? So if you solve for Fe, you've got curly EQ, you've got the field intensity times the charge, right? So that gives us this, right? We end up with the curly E and times the Q, right? And then really what's happening is that's force. I should actually have the dot up here too, actually. This is really F dot R, which you remember from the previous unit, it's a dot product, right? It's how to multiply these things, these vectors. Right? It gives you a scalar quantity, which, it's energy. Of course it's going to be a scalar, right? So it's all making sense. And recall that, of course, work done is change in energy, and energy equals QV, right? So delta V, remember, change in electric potential difference is energy per charge, right? Energy per charge, the charge would multiply up on the other side, giving you this. So this is that familiar equation of delta V is from over here, I guess, right? Delta V equals, where was it? Anyways, we just looked at it recently. Here. Yeah. So put those together and you've got this. Notice that the Q's can just cancel out, right? So just try and show that there, Q and Q. And so we're going to end up with the delta V equals the dot product of the electric field intensity, the force per charge, dot product with the displacement, if you will, right? And so that comes out to be this if you solve for that electric field intensity. So this has been a development of that result that I said earlier. I just stated this earlier just to sort of compare and contrast between them. But this is proof, it's a development of the fact that that's the case. Here's that. That's what I was talking about before about the potential being energy per charge and so on, right? So this this Q delta V, right, is explained here. That's where that came from. Yeah, and so notice that it's a magnitude, and it means it's a scalar value, right? It's implied because the dot product is by definition a scalar, right? It's the magnitude of this times the magnitude of that, and then times the cosine of the angle between them. Previous information we've seen, right? Just to remind you of it. So potential this is, I should have done that backwards here. So this is an expression for the magnitude of the electric field at any point in the space between two large parallel plates with a voltage applied across. It's what we were looking for. Yeah, and then the electric field, of course, is from the positive plate to the negative plate because the silly definition of positive current flow. And then that delta V, of course, is that potential difference applied across the plates and so on. A little calculation shortcut for you, and we'll see this in an example later. But if say you are, if a charge has moved, 1/3 of the way across, well, because the force is constant, then 1/3 of the energy would have been transferred, if you will, right? That's what happens when a charge is moving in an electric field. Force pushes on it the whole time and it transfers energy to it, right? So the change in energy per charge, you would have gotten 1/3 of it so far. Okay, and I'll show that later as ratios as well, but just a way to get an answer if you need to, right? This was a review of, I told you before about how if you just have charges built up, then you can change the distance between, and it seems odd, the electric field stays the same, but when you move it to a farther location, you've done work there, so there's more energy. stored, right? So if you picture a negative charge repelling all the way to there, well, it's going to repel even farther, so it's going to have even more energy, and so that same force over that larger distance, makes sense that it's going to be the same force the whole time, giving that larger amount of energy, right? If you look at it as the work done and the the electric force times the distance, this work done, of course, is going to be bigger, and the distance is bigger, and in fact, they're both big by the same amount, right? And so you can see that the electric force would be the same the whole time. Okay, so that is that. So this is as long as they're just charged plates. Oh, also as long as the area of the plates is large relative to the distance between, and so on, right? So the contradiction, like it seems like a contradiction, right? Most textbooks don't really talk about this a whole lot, and so I was actually pretty confused about this for a while, and I found myself searching, like, okay, does R matter or not? The answer is yes. It just depends on the situation, right? So the field between a pair of charged parallel plates, no voltage applied across, right? There was a voltage at some point, I suppose, getting charges to, be there, or maybe even just statically put them on there and rub blue on your head and then touch it to the top plate. But anyways, the electrons are all just trapped there, right? And so, we know in this scenario, the logic is that the distance between the plates doesn't matter. But we have this new equation that's saying, or in this new relationship where it does matter, and it's odd, right? So this is my favorite line here. It's like, if the battery voltage creating the charge separation in the plates is kept constant, then the distance between the plates will indeed affect the electric field intensity, since the amount of charges produced on the plates will vary with the distance between. What that means, if you can think of it that way, is that batteries can't keep the electrons pushed that far apart, right? As you're moving them away, electrons will spill or flow back into the battery. The amount of charge doesn't stay constant in that scenario, and that's just not an obvious thing. If the plates aren't connected to anything, then they're disconnected. Then the charge can't go anywhere, and so it just forces them to stay there. Right? Capacitors are an application of this. Parallel plates with just a bunch of charge built up on them, right? It's a way of storing energy. So you get a bunch of electrons built up on one side, and then when you connect it, you allow them to rush through a flash bulb, if you will, an old style camera, or any camera, I suppose, right? Capacitors. They're also used in air conditioners. They're a little boost of energy to help the end motor get going at first. So if your air conditioner stops working, quite often it's just the capacitors malfunctioned. And so, yeah, like part of the trouble with these two concepts is that they're so similar, but there's this subtle difference in a pretty different result as a result of that subtle difference. Charge just being built up versus a voltage being applied across. Because either way, you've got like one's negative, one's positive, right? So you just kind of have to just I wish it would be a little more clear. When I'm reading the questions now, it is more clear to me. But oh well. It's possible confusion, right? So right here is where it's more clear to me now, right? So potential difference between two points on two parallel plates. Right away, potential difference. That means a battery is connected. But I wish it would say that. It's like a battery is connected, causing a potential difference of, rather than just saying charges are just built up on their own there. Anyways, so the way the math works, of course, we have the equation was delta V over R, and they gave us a delta V and an R, so just calculate it out, right? So just keep in mind, of course, that this curly E we're talking about, when it asks for the magnitude of the electric field strength, first of all, recognizing that means they're looking for curly E, right? That's something to not pay attention to. That is not necessarily obvious to everybody, right? That is meaning that. So yeah, recognize that, and then just run the numbers, right? So when you get it in the end, you're thinking, okay, well, that's the number of newtons of force that each coulomb will have on it, right? It's newtons per coulomb. Have those concepts make sense to you? It's not just a bunch of letters and mystery. So do the units make sense? Do they match up with what they should be? Electric field intensity, of course, should be, as I just mentioned, force per charge, newtons per coulomb, and it's written as delta V over R. And you're like, that doesn't look like newtons per coulomb, so let's analyze it. We're going to convert to SI, Standard System International Units, right? Meters, kilograms, seconds. And so if you look at delta V as a concept, that's energy per charge. So that's the first thing, energy per charge. So then you're like, okay, that's energy. the joules is energy. Energy is work done, right? Force times distance. And force is newtons, and distance is meters, of course. And then newtons, think of like Newton's second law. F equals ma. It's mass times acceleration. So we have mass times acceleration times meters. So watch here. Okay, this one is you have a touchscreen on my laptop, but it doesn't work great. But let's just point out this one right here is meters. Sorry, the touchscreen's so terrible on my laptop. And then the other one's mass, right? And I suppose I should write that into. I don't want to though because it's so hard. But that one's mass. The old laptop had a pen that worked way better, but no pens with the new ones they gave us. Anyways, yeah, so that's going to be kilograms. And then acceleration is meters per second squared. And obviously still have the meters there. And so we end up with kilograms. Meters times meters is meters squared. So we get kilograms meters squared per second squared. Boom, there it is. Right? So this m canceling out business, it's not squared anymore because there's a big old divide by m down there. Notice I'm trying to communicate really well. When you have fractions over fractions, it's fractions as part of fractions. It's tricky, so I'm isolating that top fraction with the red bracket for communication. So that m can cancel out with the m's, the one of the m's there, right? And so that just gives us kilograms meters per second squared. And if you analyze that thing, kilograms meters per second squared is kilograms times mass times acceleration, which is force. So it's newtons, right? So this, in fact, does absolutely equal. It's completely equivalent to newtons per kilogram. Analysis like that later on too will be necessary when you think of the two different versions of the mass of electron later in this course. The mass of electron can be given as a certain number of kilograms, 9.1 times 10 to the negative 31 kilograms, or it can be given in mega electron volts, MEVs, which is 0.511. But those two things are absolutely equivalent. It's weird that mega electron volts, which certainly sounds like energy-ish, right? It is energy, and anyways, but that is because of E equals mc squared, right? And mass and energy are equivalent. So yeah, I remember in university realizing, like, wait a minute, I'm all of a sudden I'm comfortable with using mega electron volts as the mass, and I'm like, oh wait, so apparently E equals mc squared is true. I'm all of a sudden doing it intuitively or without having it be weird to me. So here we go. Just some parts of these are easy where it's just the concept, right? So it says, this negatively charged plate set up the way it is. From the electricity unit in grade 9, you might remember, and I think I showed it earlier here too, but that small side, you can think of it as a negative symbol. That's the negative. So there it is, making that charge plate be negatively charged. The other side is the positive, so positive charge. So we've got this applied voltage situation. Question is, would a negatively charged particle that's allowed to move freely in this apparatus, which way would it go? Well, of course, it would repel from the, right? So these arrows are showing the way a positive test charge would go. They're showing the direction of the uniform electric field, right? The direction of the force would be per coulomb on a positive test charge. Because it's a negative, it's going to go the other way. Next here, where will it have the most electric potential? First, we have to remember, what does electric potential mean, right? And that means energy per charge, right? Energy per coulomb. And so where's going to have the most energy? Well, a negative charge down here would have the most energy because it has all of that push available to push it all the way, right? So that down here, which will travel, it's going to have at plate B, right? Because it's has lots of force available, right? That's so it gives the electric potential energy stored and available to be released to kinetic energy. It will accelerate as it repels from the negative plate. All that stuff we know, right? It even points out in the solution here that at plate A would have zero potential. It's stuck to the plate, right? Next, where will it experience the greatest field intensity? So what is field intensity as a reminder? Well, field intensity is force per charge, right? So newtons per coulomb. where is it going to have the greatest force? Well, of course, it would be when it's here, right? It's going to have the push on it. Oh, actually, no, that's not true. That it would have the most energy there, but remember, the force is the same everywhere, right? So the reason I just kind of clued myself in, but I was thinking, wait a minute, if it was stuck to the plate here, there's going to be a force on it. Here, there's a force, Nick. It's the same everywhere. Okay, so take my my oopsie there and use it as a tool to help remember, like, okay, this can be tricky, right? You gotta keep clear on all these things. So yeah, absolutely, the answer will be that it's the same throughout. Number 4, if the potential difference between the plates, if the potential difference between the plates is 120 volts, and it's weird too that if the delta V, right, if the triangle V is equal to 120 V, it always bugs me, right? But I hope it's clear enough to you because of how I've helped you with this. Anyway, so at what point will the charged particle have experienced a potential difference of 40 volts? This is, and press pause, of course, right? If you take a chance to think about these things, be an active learner, but I'm trusting you're just going to do that as you go. I forget sometimes to say it. So anyways, this is to do with that fraction of the voltage equals the fraction of the way, right? So, at 40 volts, right? Well, 40 out of 120 is 1/3. So pretty easy just to say, it's 1/3 of the way, right? It is kind of nice to think of this as a ratio situation where you can have you can have the fraction versus the whole. So the 40 out of the 120 is equal to, the fraction of the way in comparison to the whole way, the 1, right? 1 represents like 100% of the way, if you will. Whereas the 1/3 represents 33% of the way. So 0.33 equals 1. Anyway, so there's your potentials ratio and your distance ratio. And of course it works out, right? So going from second to first, you do the second divided by the first is your multiple. It's the same thing. It's 40 divided by 120. I think this is probably the cleanest, simplest way to do it. But I always like to point out ratios whenever they can be used because they are super handy when it is hard to understand, or and everybody has found themselves at one point saying, wait, do I multiply by 100 or do I divide by 100? Ratios is your way of getting that answer every time. If the distance between the plates is reduced to 1/2 of the original value and the resulting electric field strength between the plates is 6.5 times 10 to the 5 newtons per coulomb, electric field strength, that's curly E, right? Yeah, so okay, electric field intensity. Yeah, so electric field intensity, for parallel plates is delta V over R, right? And of course, field intensity is force per charge, right? So just to clarify the concepts and what the numbers are for the situation. So we are going to figure out the original field strength first. So we're at 1/2 of R, right? So it's going to be, it's reduced to half the original value, right? So we can think of it as this, right? This is the half the original value. So we say, okay, well, the electric field intensity here. So if we go and say, okay, well, the electric field intensity is double because when we divide by that 1/2, basically we're finding out that the electric field intensity is now double. I don't know if that's entirely necessary for everybody to do, but the idea that when you make the plate distance between the plates be half the original amount, that the field intensity is going to be double. But it's important to know that, so I'm showing how that would be determined if you weren't sure, right? I think it's kind of obvious, like since the electric field intensity is the voltage divided by the distance. Well, if the distance ends up half as much, then it's basically a direct relationship kind of thing, right? So it would be double the amount. Inverse relationship, I guess, really should say. But so we have, anyways, the original must be 3.25, right? So then we can say, well, what's the distance? Well, at that point, it's just using the equation, right? So we have the 3.25 times 10 to the 5 equals 120 per R, and we just solve for R. All right. And Millikan oil drop experiment. So the Millikan oil drop experiment. So I want you to think through a little activity here. So press pause, and oh boy, and look at this thing here. So it says, if you're given 10 sealed paper bags and there's marbles in each one, okay, and you know that all the marbles have identical masses, and then you measure the total mass for each one, Okay, your challenge is to figure out the mass of each marble. So you take them out, the sealed bags one by one, and just the bag is basically massless. Okay, in this scenario, and so you find out these are all the masses of all the bags, and you're being asked what's the mass of each marble. So press pause, think about it, try to come up with an answer for what you think the mass of a single marble would be based on those numbers. Okay, I'll throw in some other numbers later that would make it more obvious, but for now, that's all there is. Okay, that's what you've measured, and it's more realistic for the actual experiment. So, given this data, what's the mass of one marble? Explain your thinking. Okay. I don't have much of a hint here, but the marble's going to have like a whole number mass that eliminates some other possible answers. So, what would you be trying to do? Well, you'd be trying to break these numbers into you want to say different numbers of the same thing, or you want to think of these as, this could be four groups of four, and then this is a certain number of groups of four, and this is a certain number of groups of four, and this is a certain number of groups of four, right? So really what you're going to do is you're going to see like what numbers can divide into all these as a part of that, right? So 4 can divide into some of these, but not all, I don't think. And so really the conclusion you should come to is it's either 1 gram or 2 grams, or it could even be like half a gram, things like that. But it's likely that it's 2 grams since there are no odd number measurements. If 1 gram was possible, then something like 13 would be possible because you'd have 6 of the you have that extra 1, right? So if you don't have a 13 ever, it's likely the 2, right? So again, like I said, if there was other numbers in here, like 2 grams, for example, that would make it more obvious. And if 4 grams was in there, and if 8 grams was in there, and basically you can see like a whole bunch of different values. And oops, that was supposed to be a separate one. Anyways, right? So that would make it more obvious because you'd actually have the 1. But I mean, that's not likely. I don't think it ever happens with the charge of an electron. So the way it was given is more realistic. So yeah, the thought process carried out in that activity is meant to represent the process that Robert Millikan did during 1906 to 1909. He was staring through, I'll show you what it looks like, the apparatus for a 3-year period in his basement. Everybody's like, dude, come on outside once in a while. But yeah, he was studying this and thought he was onto something and worked hard at it and has his name on it as a result, right? So after observing a very large number of these small quantities of, you don't even know what it is yet, right? The Millikan oil drop experiment. This statement will make more sense. Okay, small quantities of tiny oil droplets. Millikan found that all the charged quantities were a multiple of 1.602 times 10 to the negative 19, which, of course, as with the advantage of modern education, modern society, you're just taught this, but this is how it was discovered, right? And so based on this, he correctly concluded that the charge on a single electron is that value. And he also correctly concluded that that's the smallest amount of charge possible. At the time, later in this course, we're going to talk about quantum theory. But at the time, 13 years or so before he had done his work here, a German physicist, Planck, had discovered that energy is quantized. So energy can only be in certain bite-sized pieces. There's a minimum you can have. And so it was pretty natural for him at this point to say, oh, okay, well, that's, charge is probably quantized too. You can't have any small, there's a limit to how small of a chunk of charge you can have. Just like it turns out, even weirder, there's a limit to the smallest chunk of energy you can have. And again, we'll see that later, of course. So these little oil droplets, this is the experiment, right? You have these charged parallel plates. That's the connection to this topic. You have these little oil droplets in there, and what they're you poof them out through like an atomizer. It's kind of like really the same thing as a little perfume bottle. You ever seen a perfume bottle with a little rubber bubble, and you squeeze it and it puffs a little air, and then some perfume gets drawn out and sprayed out into little droplets? Exactly that. Okay, a little bit of oil, droplets get poofed into here, and then those oil droplets want to fall due to gravity, but you adjust the voltage on the plates to prevent that, right? So if you have negative plates at the bottom, then it's going to repel any droplets that happen to have picked up some some negatives. I can't really do this very well because I don't have the touchscreen, but the little nozzle of the oil where the oil droplets are coming out. You've got little droplets of oil coming out of here, right? And on that nozzle, there's going to be a bunch of negative charges because negative charges repel, right? So they always repel to points of objects. You might remember this from the static electricity unit in grade 9. So these little negatives, they're repelling from the other negatives, right? And so as an oil droplet is coming out, it's likely they tend to pick up some negatives, right? So these little oil droplets are floating through the, sprayed out and they're traveling through the air. And there's a darn good chance that there's really a bunch of excess electrons on them because of that situation, right? So they have a net electric charge, and that's what I'm going to show you how you figure that out, right? So it's So the steps, oil droplets were sprayed through a fine mist atomizer, and they go through a small hole in the upper plate. They fall down in, and then the plates are oppositely charged, and so you adjust the voltage until the oil droplet. Really, what you do is you adjust it so that it falls at a constant rate. But a lot of people say you adjust it so that they are stationary, which I've done the experiment, so I remember what we did. But this is possible, of course, because of the charge on the bottom of the plate and the electric force repelling against the gravity force. So that's going to be key in our discussion, right? We're going to have the net force on the oil droplets is going to be the electric force and the gravity force. And we're going to want to have an acceleration of 0, so a net force of 0. So really that leads to, since this thing here is 0, right? Let me just do that 0 equals, right? Situation here. Then you can just, subtract gravity from both sides, or however you want to think of the adjustment. But really the sizes of these things are equal as a result, right? As we've always done with net force equals 0 situations. So that the electric force would match this equation, right? Remember, curly E is force per charge, and so we're just multiplying charge on both sides. So Fe equals Q curly E, and then force of gravity is mg, right? So we have this equation, QE equals mg. The electric field intensity for parallel plates is the voltage applied across divided by the radius, right? So we have then this, right? This piece here getting substituted in, right? Getting substituted in right there. So yeah, we get Q delta V over R equals mg. And so you rearrange that thing and you get Q. And so all you have to do is, I say all you have to do because it's not super easy, but you just have to figure out the mass. You have to figure out actually just the mass pretty much. Yeah, you have to figure out the mass of the oil droplet. And then G is 9.8, R is the distance between the plates, voltage is the voltage you're applying. When you're measuring the mass, though, it involves some estimations. You have to estimate the diameter of the oil droplet, and then you use the density of the oil that you're using, and you figure out the mass. Okay, so the more accurately you figure out the mass, more accurately you know the distance between the plates, more accurately the voltage is being applied at. All that's going to give you a more accurate measurement value for the charge. And then again, you get a whole bunch of values like this that are all happen to be multiples. Now the smallest multiple might be 10,000 or something, right? It's not like you're going to have an oil droplet with just one electron, but that's why the Coulomb of electrons was invented, right? As a thought of as a way of talking about amount of charge, because there's just so much charge involved all the time. But that'll give you the value. So this video here, Millikan's, I'm going to play that one. This will give you a good visual of it. Yeah, I was thinking, oh, I'll just play from my downloads, but that's on my other computer. So go to videos. I'm going to type in oil drop, and oil drop, and the one I want is the one larger amount of wording. Yeah, All right, here we go.
Millikan's oil drop experiment. British physicist J.J. Thomson had measured the ratio of electrical charge to the mass of an electron using a cathode ray tube in 1897. Later, R.A. Millikan looked to determine the charge on the electrons. The famous method that he devised between 1906 and 1914 to measure the charge E of an electron.
So there's the mist of oil droplets. There's the oil droplets fall down through a little hole. Here's a little stream of oil droplets, and then you're adjusting the field to make them fall at a constant rate.
Is known as the Millikan's oil
there's the
experiment.
little perfume.
Using this
squeezer,
method,
right?
he calculated that the charge on an electron was about 1.6 times 10 power negative 19 coulombs. In the Millikan's oil drop method, an atomizer produces oil droplets in the form of mist, which are sent through a plate of electrical condenser. There are different forces which act on the oil drop, including gravitational, electrostatic force due to electric field, and viscous drag force.
Viscous drag force. I'm trying to remember if we accounted for that at all. I don't remember. We probably did a long time ago.
The rate at which these drops fall were measured by observing the micrometer eyepiece of a telescope. X-rays.
So you're peering into a microscope, basically, and seeing little droplets
through the chamber to ionize the air inside. On colliding with gaseous ions, these oil droplets acquire charge.
That happened at the tip. I don't know why they're talking about it there, but
the rate at which these droplets fall can be controlled by changing the strength of applied voltage to the plate.
Okay, so that's the basic idea of it. And the other one I want to show you is this one, like what it actually looks like. So Millikan, I did this for several hours on one of my Thursday labs at university. Millikan did this for 3 years, apparently. There's little oil droplets that were sprayed in, and you adjust the voltage, right? So you adjust the voltage, you can make them move up. Too much voltage, and whatever. So that's what you're doing. And you want to get the voltage set just right, that the drops just go at a constant rate down. Just one sec here. All right, so you decide to set out to replicate the Millikan oil experiment by assembling two parallel plates that are 5 centimeters apart. You got a small spherical oil drop whose mass is this, which again, that's tricky to get, but they're just giving it to you, so you're welcome. There's a voltage between the plates of 120 volts. Whew. That's hot, but oh well. And you decide to make the top plate be a negative. Okay. What? Oh. What charge must be on the oil droplet? That wouldn't be normal. But anyways, what charge must be on the oil droplet then in order to have this work, right? Well, they're saying that you'd have to have a positive charge, right? Because then if the bottom plate's positive, you'd have to have a positive charge. So you'd have to have oil droplets that are missing some electrons, which I suppose is possible. I don't think that's typically how it would work because of this diagram that I showed, wherever it was, the little nozzle with the electrons repelling and jumping onto the oil droplet. That's typically the way it goes. But oh well, textbooks are silly. So what is the magnitude of the charge on the drop? Okay, so we know, as we talked about, that the gravity force and the electric force have to be the same. That's what we're shooting for when you're adjusting the equipment. I was going to show you before that. The electric field we know is from electric field intensity in a system, so that's force per charge. So if we multiplied both sides by Q, that thing can become Q curly E, right? Charge times the force per charge. So we have force equals force, right? After that, this is just a result. After that, you'd say, okay, well, what's curly E? Well, curly E is delta V over R, right? So delta V over R. And so we get that same result, that Q mgr over delta V, right? This is another example of where, you don't want to just take that equation that ChatGPT is going to spit out at you. You're analyzing physics, right? So you're doing the physics work, and then you're getting a result. So here, you plug numbers in, and boom, you get your charge. Okay, so it says the charge on the droplet was the positive 4.1. Okay, so even though it says this is a tiny electric charge, it represents a deficit of about 3,000 electrons. That wasn't really supposed to be said yet, because the next question is, how many is it? Is it an excess or deficit, and how many? Well, obviously it's a deficit because it's a positive charge, right? So you can look at it as Q and E, right? Or you work on it based on the knowledge that a single electron has a charge of 1.602 times 10 to the negative 19. This is definitely my preference, right? It's just knowledge of key concepts like the charge on an electron, for goodness sakes, right? So I'd much rather you think of it that way. So I'm going to go this way first. So that would be the ratio then of number to the charge, right? Number of them in the charge. So we have a known 1 is this, right? Amount of charge, and this is the amount of charge we have. And so when you go from, you want to be able to look at the multiple from this side to this side. And so it's going to be second divided by first, right? So it's going to be multiplying by second divided by first. And so you just essentially just divide that thing by this and you get transferred. Here we would say, oh, in this equation that may or may not mean something to you, you're solving for n. And so you end up with q divided by 1.602 for some reason. I feel like you can possibly have less of an understanding of what the heck you're doing by using an equation. Certainly, like I would say, if you're using it blindly, that's just terrible. It's too much to try to memorize and blindly use, right? So for this unit especially, I've said it lots of times, try to make sure to try to have a key concept or a key full understanding of what the heck you're actually talking about. It's not just Q's and V's and triangles, right? So there's that almost 3,000 electrons that it's missing. So that is that. So as usual, your practice assignment, and if you have any questions, don't hesitate to ask. And yeah, thanks for watching.